And this is the first lesson in our sort of study of calculus we're going to look at. Because it's just a brief introduction to calculus, we're not going to go really in depth into a lot of the ideas, just sort of surface knowledge, but there is a lot of kind of new language and new ideas we need to talk about. In particular, in this first lesson, there's going to be a lot of words and theory. Okay, so the idea of calculus is we want to examine rates. Hey, how fast something is moving, growing, changing, costing, how things are changing is our big idea. And calculus really is the study of rate of change. So we'll start off with the idea of a graph. When you look at a graph, you can see that it's changing. It might be going up, might be going down, it might go up and then back down and then back up again. And we can often see where that changes. How things are changing, how the two variables relate to each other is considered our rate. So for example, in this graph here, we have a relation between distance and time. Okay? Our distance is changing over time. Well, we often refer to that as speed. Okay? But really that's just the rate of your two variables, the difference between distance and time and how it's changed. Well, if I want to calculate the rate, we can figure out the difference in our x's, actually here, typo there, difference in our y's over difference in our x's, and that would give us our speed, our slope in other words. Slope, rate are interchangeable words for the same thing. And for us in IB, the word gradient will also come in there, the gradient of your line. So we're always thinking back to slope. Okay. For linear relations, nice straight lines like the graph we looked at, rate is really easy to find. Calculate your slope, you got your rate, because it's always the same. That line is going down the same amount. I can extend the line, and what's going to happen? It would do the exact same thing all the way down. Right? My rate is constant. But for nonlinear graphs, ones that go up and down and back up again, rate's a little bit more tricky to figure out. So you might recall from higher functions last year, we talked about AROC and IROC. Our average rates of change. Okay, so that's your rate of change between two distinct points on a graph. We call that the secant. So in this example, from A to B are two different points. If I find the slope of the line that joins those 2 points, I've figured out my average rate of change, my AROC, my average speed, if you will. Or I can find an instantaneous rate of change, the IROC. Okay? Its rate of change is the slope of the tangent. That's this blue one here. A tangent is a line that just touches a curve at a single point. So there's all kinds of tangents we can find, but the one thing that has to be true is they touch at just a single point within a small range. Okay, so we have two different ways of looking at rate when we look at nonlinear relations, and that's kind of what we're going to do in calculus, the nonlinear functions. We either want to do AROC or IROC. So let's look at an example. We've got a cyclist leaving an intersection. They're cycling away. So at the beginning, there's dead stopped, right? Over time, they're going to pick up speed. The graph is going to start curving up like it does. They're getting faster and faster and faster. We want to figure out a couple things about this graph. We want to know the average rate of, the average speed over the first 5 seconds. So our speed, because it's over the first 5, is actually an AROC, an average rate, 2 distinct points. I've got to figure out what's happening at the beginning, so 0, 0, up to what's happening at the end, 525. So my speed will be the steepness of the line that joins them. In other words, y2, which is 25, minus y1, 0, over x2 minus x1. That gives me 25 over 5, or in other words, just 5, and our units here are meters per second. Over the first 5 seconds, the cyclist is going, on average, 5 meters a second. Okay. You try the next one, see if you can figure it out. I want the AROC between 2 and 5, the average speed. Again, it's AROC because they're 2 distinct points. So we're going to have to estimate here a little bit, right? What's that 2? I think 2 is approximately right about there. And the value's at 2 because my grid's a little bit hard to read, which often happens with graphs, and that's kind of one of our issues. Let's say it's about, I don't know, 5. Okay, so now I'm going from 2,5 to 525. Again, same formula, right? y2 minus y1 over x2 minus x1. We get 20 over 3, which is approximately 6.66 meters per second. So in that small section of the graph, they're going faster than they were on average. Let's try the next one, between 4 and 5. Again, we're going to have to estimate. Here's 4. What's the rate of change between those two dots? That's what we're doing. Just going to erase the line and talk about the numbers here. Okay, so my point for 4, if I guess, I'm going to say it's about 16. Let's call that 16 there. Okay, so this is number 2, or part 2 of letter B. Our speed this time, again, y2 minus y1, so 25 minus 16 over 5 minus 4, 9 over 1. Hey, they're going 9 meters a second. They're faster in the section from 4 to 5. And if I were to put the lines back on, just for our lines here sake, that line and the next line, well, those aren't quite the same steepness. The red line's somewhat steeper, not a whole lot steeper, but a little bit steeper, which kind of matches what's happening with our values. Okay, let's try the last one. I want to find the AROC, average rate of speed, between 4.5 and 5. So 4.5, we'll call it right about there. 4.5, and that's right on the line, so we'll call that 20. So for part 3, our speed equals 25 minus 20 over 5 minus 4.5, which gives us 4.5, or 10 meters a second. Just a little bit faster again. Again, that line is just a little bit steeper than it would have been in the first place. So it appears the closer I get to 5 seconds, the faster the cyclist is going. Okay, we start off at 6, and 9, then 10. Well, the last part says, how fast are they moving at 5 seconds? As I was just saying, random guess, I'd say, well, they're going slightly more than 10, right? It seems to be getting closer and closer to 10, the closer and closer my dots get to 5. But if I actually want to figure it out, if I want to figure out what's happening at 5 seconds, I need to find out my instantaneous rate of change, my IROC. My speed there, well, because it's only a single dot, a little bit hard to find the difference between them, so I need to draw a line. I need to draw a line that goes through the point 5 and 25. I gotta try to make it a straight line here, just touching there. Now that's a little tricky to draw. I have to do my best. I'd use my ruler and say, well, I think this is about, I don't know, about 2.6 and 0. This point up here is about 8 and, well, it's pretty close to 60 there. Let's call it 60. And actually, let's make this one 2.5. That's pretty much in the middle. Now, you notice if you have looked at the lesson that went along with this, the numbers that I just wrote down and the numbers on the sheet are slightly different. When I drew my line the first time, I angled it slightly different than I did this time. That's kind of the problem when we talk about graphs, right? So let's find our IROC, the steepness of that last line at 5. What do we get? We get 60 minus 0 over 8 minus 2.5. That gives us 60 over 5.5, which is approximately 10.91 meters per second. Hey, we had a pretty good guess when we said slightly over 10. Turns out it's 10.9, but we didn't know the exact thing. Now, I'm hoping you've noticed the problem I just came across. AROC wasn't bad. Okay? Those points, I could estimate them not bad, and there was going to be a huge difference. But IROC, if you were to draw your line, you said to yourself, no, I don't think the line was there, Mr. Casella. I think it should have been like, oops, not right there. That's definitely not on. Okay, well, I thought the line should have been right here. Well, then your number here is slightly different than my number there, right? And the more differences we have in our things, the more problems we're going to have in our instantaneous rate of change. So while graphical method is okay, by eye thing kind of throws us off. Okay, so to fix this, we're going to develop ourselves an algebraic model. Okay, because if we use algebra, using numbers or plugging in values, well then we can always get the exact same answer, whether it's you do it or whether I do it, assuming we both don't make mistakes, of course. Okay, so the name of our model, we're going to call this the gradient function, the steepness function, the slope function. Okay, I want to find the slope of this line, the slope there, the slope there, the slope there, the slope there. I need to make an equation that will find all those slopes for me. Okay, we're going to call that as the gradient function. We are going to also call this, and this is a big calculus word here, part of our terminology, the derivative. And the derivative is your gradient function. It's the thing that's going to allow you to figure out the slope at any point on your curve. All you'll have to do is say, oh, I want to know when x is 3, what the slope is. No, when x is 0, what's the slope? When x is negative 2, oops, what's the slope? Okay, it's going to give us an equation. We like equations to help us figure out slopes. So a little bit of notation for you. We're going to use f prime x, that little dash up there is a prime symbol, or y prime, or dy dx. That stands for the derivative of y in terms of x. Or in other words, how y changes depending on how x changes. Okay, in other words, our rate. Okay, so we're going to use all three as kind of interchangeable. We'll go through a couple examples and you'll see how that works. Okay, how are we going to develop this relationship? Well, we're going to start off with a familiar function, a quadratic. Okay, I got a whole bunch of graphs down here on the bottom of the board with quadratics. And nicely for us, someone's drawn in our tangents. They've drawn in the tangents to our parabola. Here's our parabola, just half of it. Okay, the other half would go here, right? They've drawn in the tangent at certain points. So here's the point where x is 3, and here's the tangent drawn in for us. What I want to do is I want to figure out the slope at that point. So my slope, my line, or a triangle here, it has to go down 6 every time we go right 1. So my slope is 6/1, or just 6. Now, hang on there. I messed something there. It's going down, right? So it should be down 6/1, which is -6. Kind of important science. So look at the next graph. This one's the tangent at -2. Here's -2, and you can see the tangent line goes right there. The steepness of this is down 4. Right 1. Well, down 4, right 1 is -4/1, or in other words, just -4. And try and work ahead if you can. Find me the slopes of the next 4. And just pause it for a second. Okay, the derivative of, sorry, the slope of the tangent at 1. I have to go down to right 1. Down to right 1. That's -2/1, or just -2. And the slope of the tangent at 0, that's kind of nice. Tangent at 0 doesn't go up or down, just goes across. So no up or down, just to the right 1. How do I show that? Well, 0/1 just comes out to 0. We try the next one, the derivative of the tangent at 1. It's got a slope of up 2/1. And if we try the last one, I'm hoping you figured out it was up 4 over 2, which is 2. Oops, not over 2, over 1. Up 4/1, which is 4. Okay, now obviously I didn't put the 10 one on here. The graph doesn't go to 10, but I should be able to figure out that there's a pattern. Our whole objective in this part of the lesson is to figure out an equation that represents the steepness at any points. So if I've given you some points, and we figure out their accompanying steepness, what's the pattern between these things? Well, it looks like I can take the x value and I can double it. So in other words, the equation, the derivative function, our slope equation, our IROC equation, our gradient equation, all the same words, okay? For the equation f at x equals x squared, that's just our basic parabola, turns out to be, here's our notation, this means the derivative function is just take your x and times it by 2, just double it. Okay, so based on that, if I want to know the derivative, the slope at 10, I can plug in 10 for my x into the equation, and I'll get 20. And sure enough, if I were to graph it and draw my tangent exactly right, you would get a slope of the tangent being 20. Okay. Now, this is kind of like an investigation. Here's the rule. For any polynomial, we call this the power rule, okay? For any polynomial in the form y equals x to the power of something. For instance, our last one was y equals x squared. Its derivative, its slope, its gradient function is always given by y prime equals n times x to the n minus 1. Well, what does n stand for? N is the exponent. So if I want a derivative, I take my exponent, I put it down in front, so the number 2, times x to the power of, what was the exponent? It was 2, right? So 2 minus 1. And it's always subtract 1, okay? Which simplifies to just 2 to the x 1. Or, if you will, just 2x. Like the thing we guessed a second ago. So what does that mean? Well, that means if I get more complicated functions, like this example here, I can find their derivatives, their slope of the tangent, very quickly. How am I going to do that? Well, let's look at part A. I want my derivative. My derivative is, notation here, y prime, the 8 comes down in front, times x to the power of, I take my exponent and subtract 1, so 7. There's a function that will define the slope at any point. If I want to know, if I'm given a point, what x is 2, I just plug it in and get my answer. Let's try the next one. Y prime, 5 comes down in front, x to the 4 now. Subtract 1 from your exponent. You try C, y prime, my exponent comes down in front is a negative 2, times x. Don't forget to subtract 1. And if I take negative 2 and subtract 1, I get negative 3. Okay, the exponent's going further into the negatives. And then I got this weird one at the end here. Now, this makes our life really challenging when you have letters on the bottom of fractions. So we're going to do all we can to avoid this situation. We're going to go back to grade 11 math and think about exponents for a second. You might recall in grade 11 we learned about if things are negative on the, if you have an exponent on the bottom, you can bring it to the top and make your exponent a negative. In the previous question, when I had y equals x to the negative 2, that really meant y equals 1 over x squared. I just wrote it in a nicer form. Why did I write it in a nicer form? So I can do my derivative. And if we go back to D now, my derivative, in this case I used f, so f prime at x. My exponent comes down in front, times x to the power of, subtract 1 from your exponent, negative 7. Okay? And this is taking care of finding that IROC for us. It does all the work for us without us having to draw a picture, without us having to find slopes. It does IROC. It finds your rate, your slope, for your tangent at any point. And that was a lot of stuff. We got a little bit more to go. Okay, just one more screen here, I think. Yeah, one more screen. Okay, so some standard derivative patterns. That's really our big concept for today, finding me a derivative. Okay, pattern number 1. If you ever get a constant, and by that I mean just some number, the derivative of some number is always 0. Always, 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 always. So if I go look at the first example here, the derivative of a function is given of 3, its derivative will be 0 every single time. Okay, it's just a number. Derivative comes out to 0. If I have a constant in front of a function, for example, 4x squared, well, the derivative is the constant 4 times the derivative. Now, we could do it that way, or it might make more sense, because if I had to simplify this, that comes out to 8x, right? It might make more sense to take your exponent and multiply by the constant in front. That gets you the 8 in a single step. And with that in mind, if I look at my examples, if we're doing this one, if my function is 3x squared, its derivative will be 2 times 3, oops, I missed an x in there, sorry. 2 times 3 makes 6, and x to the 1. If I do the next one, 4 times 2 is negative 8, x to the 3. For some reason there's a minus on there, sorry guys. Okay, that's a quick way of doing derivatives. You have a constant in front. Just multiply the constant with the exponent. There's your, hang on, I'm sorry, I messed that up, guys. That's why I missed the minus sign. I put it in the wrong spot there. Negative 8x to the 3. Okay, and the last most common thing is if you have two separate functions, things separated by plus and minus signs, well, just take your derivative for each piece. So derivative of the first piece, and then derivative of the second piece. So if I have my expression, given this example, my derivative will be, well, 3x, x to the 3 comes out to 3x squared minus, derivative of this piece is 2x. So two separate derivatives, basically. Okay, so those are our basic patterns. I've got a couple here I want you to try, and then we'll try some homework. And to practice some things. So find the derivatives of the following things. We're going to combine some of these rules. So the derivative is, well, because I have different parts and pieces, I take each part and piece separately. X to the 5, 5x to the 4. Minus 3x squared becomes minus 2 times 3 makes 6x. And then over here I got a constant. The constant is 0. You don't even have to show that part. Right? There's no point putting a plus 0 at the end of something. There's my derivative. Try the next one. My derivative will be, a negative exponent comes down in front. Subtract 1. Okay, I do the 4 times the 2, I get 8. Subtract 1 from my exponent, I get a 1. There's my derivative, done. Okay, letter C. I see that letter in the bottom. We don't like that. Let's fix our function before we do derivative. Let's bring the exponent up to the top and make it negative. Okay, everything else stays exactly the same. I only fixed the first one, but I made it easier to take my derivative. What is my derivative? Oh, negative 3 times 4 is negative 12x. Subtract 1 from your exponent. 4 times 2 is 8. Subtract 1 from your exponent. And the last one, don't forget there's the number 1 right here, right? So 1 times 2 is just 2. When I subtract my exponent, I get x to the 0. Well, what's x to the 0? Anything to the power of 0 always comes out to 1. So I don't usually write this piece in. I just write the number minus 2. Okay? Or if you will, let's just erase that part. There's no x's left. I subtracted my exponent, and that part's gone. All right, last one. This one, again, I see that problem I had a second ago, the letter on the bottom. But I can't just bring it up to the top the way it is, because it's got more than one piece on the top. So I actually need to work with this fraction a little bit first. So the first thing I'm going to do is I'm going to rewrite it as two separate fractions, as in the common denominator, right? Just in the two parts back again. I can then simplify each fraction. And by that I mean, let's cancel out things that appear on the top and the bottom that are the same. For instance, there's an x on the top and an x on the bottom. Let's get rid of one of each. So I end up with 2 over x. I canceled an x from both the top and the bottom. Why would I do that? Well, made it a little bit easier, a little bit smaller. And now I notice that I've only got letters on the bottom. I can bring letters to the top by making the exponents negative. I can bring letters to the top by making the exponents negative. I now have a function I can take a derivative of. What's my derivative? Negative 1 times 2 is negative 2x to the negative 2. Subtract 1 from my exponent. Careful here, negative times a negative, positive 6x to the power of negative 3. Okay. So there's a brief introduction to how we're going to start working with calculus, in particular that we want to be able to find a gradient equation, a formula. We're calling that formula our derivative, which will allow us to find our rate of change at any point on our curve, our IROC, without having to make a graph or take a guess. A couple questions to practice. Okay, at the bottom of your page, try the homework questions. And if you're stuck, come see me and we'll work through some things together.